This question is to determine local maximum and minimum values for a piecewise function. Please subscribe to our YouTube channel Math Tutor 8285. Your subscription fuels the passion. Let's grow together. Thank you so much. Let the function f of x be defined as follows. If x is greater than 0, then f of x equals x raised to the power of 1 over x. If x is less than or equal to 0, then f of x equals 2 times x minus 1. Determine all the local maximum or minimum values of the function f. First, we start by analyzing differentiability at x equals 0. First, we consider whether the function f is differentiable at 0. When x is less than 0, the derivative of f is simply 2, since it is the derivative of a straight line. When x is greater than 0, we consider the function x raised to the power of 1 over x. To differentiate this, we first take the natural logarithm of f of x. So the natural log of f of x becomes the natural log of x divided by x. Then, using the chain rule, we find the derivative of that expression, which is 1 minus the natural log of x divided by x squared. Multiplying this back by the original function, we find that the derivative of f for x greater than 0 is x to the power of 1 over x times the quantity 1 minus the natural log of x, all over x squared. Now, as x approaches 0 from the right, the natural log of x goes to negative infinity, so the expression becomes very large in the positive direction. This means the right-hand derivative goes to infinity. From the left, the derivative is a constant too. Therefore, the function is not differentiable at x equals 0, and we must analyze that point separately for Extrema. Then, next step, finding critical points for x greater than 0. To find where f might have a local maximum or minimum in the positive domain, we set the derivative equal to 0. That gives us the equation, 1 minus the natural log of x equals 0. Solving that, we find that the natural log of x is 1, which means x equals the constant e. So x equals e is a critical point. Next step is to determine the nature of the critical point at x equals e. Now we test whether the critical point at x equals e is a maximum or a minimum. Looking at the behavior of the function x to the power of 1 over x, we note that this function is known to have a minimum at x equals e. This is supported by checking the second derivative or simply analyzing the shape of the function near e. Thus, we conclude that f has a local minimum at x equals e, and the minimum value is e raised to the power of 1 over e. After that, we check the behavior at x equals 0. Next, we look at how the function behaves around 0. As x approaches 0 from the left, f of x